The microfluidic fabrication of emulsions using T-junction microchannel. Before commencing the presentation, I'd first like to express my sincerest gratitude to the following people. I'd like to thank Ray for his constant assist and support on putting me in the right direction for this project. Also, I'd like to thank Chris, who's not here today, for his constant assist by making the T-junction devices for us to work on during the course of the experiment, and Ms. Marta for necessary lab safety conductions, and lastly, not forgetting Ms. Davina, also my teammate or partner for this research project, for her superb help and teamwork through the course of the experiment. For that, I'd first like to outline the presentation. I'll first be talking a brief introduction, and then I'll be mentioning about the project A, followed by certain literature review about the project, followed by describing the materials used in this experiment, and then I'll talk about the experimental methods used for image analysis, and then I'll be moving on to talking about the results and discussing about it, followed by conclusion, and not forgetting mentioning certain limitations and recommendations involved in this experiment. Firstly, I would first like to define what an emulsion is. Emulsion is basically a mixture of two or more liquids that are immiscible with one another. So emulsions are used in technologies nowadays, from food industries such as ice cream manufacturing to consumer products industry such as shampoo production. So, sorry. In this research project, we emphasize on the formation of droplets in a water and oil emulsion system for large-scale stability studies using a microfluidic T-junction device. And the T-junction device will be shown in the next few slides. So the project's aim was to validate the scaling equation right here. This equation was used to size the bubble droplets generated under two specific regimes, which are known as squeezing and dripping regime. So we also studied the effect of changes of viscosity of dispersed fluid on droplet size generated, but this is only under the squeezing regime. We didn't study the droplet size generated under the dripping regime. Alright, here's the scaling equation with the parameters involved. It is very important to note that this scaling equation is independent on the interfacial tension of the liquids used in our microchannel, and also independent of the viscosity of the liquid. But this scaling equation was the main focus of the experiment. It gives us a guideline of expected droplet size generated using a desired flow rate of either the continuous or dispersed phase liquid, which will be mentioned later. Okay, right here is a sketch of the T-junction microchannel. As you can see, there are two channels joining at a right angle. The main channel will be transferring the continuous phase liquid, and the orthogonal channel will be transferring the liquid that will be dispersed. And then they'll join at the intersection of the T-junction. So this T-junction microchannel was beforehand fabricated by Chris with a thin film of polydimethyl xyloxane, also known as PDMS. Now this was just to help us to fabricate our observation of the water and oil system, either visually or under the microscope. Now, inside the microchannel, there are three forces that play vital roles. Firstly, there will be the shear force. This shear force will be exerted by the oil stream on the emerging droplet downstream of the main channel. And there will be a Laplace force inside the droplet. This was due to interfacial tension. And we have a growing upstream pressure in the oil phase. Right now, we mentioned talking briefly about the mechanism of droplet breakup. So, droplet breakup, the droplet can break up under two specific regimes known as the squeezing and the dripping regimes. So, under the squeezing regime, the Laplace force dominates over the cross-flow shear force. Having said that, the pressure upstream of the main channel, pictured on the far right over there, exerts upon the droplet, and then it breaks, and then the droplet will break out from the T-junction as soon as the fluids intersect. So as soon as the emerging droplet travels downstream of the main channel, it occupies the entire channel of it occupies the entire main channel. Therefore, the cross-flow shear force acting exerted upon the emerging droplet is low as compared to the dripping regime, because the gap between the channel and the droplets are filled up. And under the dripping regime, the cross-flow shear, this emerging droplet does not occupy the entire channel because it travels faster due to higher flow rates of oil and water use. So the cross-flow shear force prevails over the pass force inside the droplet. And right here are the materials used for experiment. We use canola oil, uniform water. We use polyglycerol, polyricinoate, also known as GPR, as our emulsifier. And we also use sucrose. So for our continuous phase liquid, we use canola oil with 3 weight percentage of PGPR. Now PGPR is an emulsifier mainly used in the food industries. So we use this PGPR in addition to the canola oil to minimize the interfacial tension between the oil and water system. Now this was mainly just to create more stable emulsions. We added sucrose into water in the later part of the experiment to study the effect of the viscosity on the dispersed phase liquid in relation to the scaling equation. So we used 20 weight percentage of sucrose and 50 weight percentage of sucrose with water. Right here are the instruments involved. We use 2 of these NE1000 single storage pumps, and then we use 1 milliliter thermal syringes, which will be connected onto the pumps and will be also connected to our T-junction devices. And then we have the microscope used was a Nikon Eclipse EV2000 universal microscope with 20 CCD cameras and 20 times magnification was used. And this microscope with the attached camera was connected to a computer where we use a B++ demo program to capture the images of the droplets or bubbles created. Right here is the method for our image analysis and observation of bubbles created. Firstly, for droplet generation under the squeezing regime, we use a direct measurement using a B++ demo. So having said that, we connect the T-junction device onto the microscope and then observe it. Then we capture live images of the emerging droplet at the T-junction. Now, as soon as the emerging droplet breaks out from the T-junction, as shown on this picture here, we capture this image, we paste it on microscope pane, simply draw a line from one end to another of the droplet to measure the length, to measure the pixel measurement of the length of droplet. Then before that, we calibrated the pixel measurements and converted back into physical measurements in micrometers. Another approach was used because the flow rates used for the continuous phase and dispersed phase liquid to generate droplets under the dripping regime were relatively faster. So instead, we collect emulsion samples in a very small vial. Now we collect these vials and we observe the emulsion samples on the vial, and this picture on the left here shows the image of the samples of the emulsion. So we simply capture this image. In order to find the length of the droplet, we use this relationship equation right here. So the volume of sphere is simply the volume of the bubble, the size of the bubble, the volume of the bubble generated, and the volume of cylinder with 2 sphere is regarded as the volume of the droplet. We regard the droplet as a cylinder with 2 hemispheral ends. And using this equation right at the bottom here, having all the geometries of the main channel constant and having the diameter of the sphere, we can calculate L, which is the length of droplet. Now this approach was also used because the image capture and for the droplet generation under the dripping regime was unclear. As you can see here, because the flow rates used were faster, so it travels faster downstream. Right now we're moving on discussing the results. you can see here there is a homogeneity in sizes of bubbles created under the squeezing regime. Now this is because the flow rates used were, as mentioned previously, slower, so the bubbles in the emulsions tend to be more stable. And next slide shows volume specific sizes for the bubbles generated under the dripping regime because higher flow rates were used. Therefore, it contributes to the fact that the bubbles may coalesce with one another, having one bubble size bigger than the other. Right here is a straight line relationship between the dimensionless length of the droplet against the ratio of the viscous phase liquid and against the continuous phase liquid. As you can see, this result here shown is linear straight line relationship between the two ratios. This is in agreement with our proposed scaling equation previously, and having said that, an increase in the ratio of dispersed phase liquid against the continuous phase liquid will definitely lead to an increase in the emerging size of droplets created. And here is the model generated for our experimental results. Here's a comparison with the from our experimental results with a theoretical estimation using the proposed scaling equation, but with an alpha constant of 1. And this theoretical estimation equation is shown on the blue one here. So you can see it's pretty much similar, and this validates the fact that we can use the scaling equation to predict size generation under the squeezing regime. Now this here is the same graph, but it is on the dripping regime, but it is on a logarithmic scale instead of a linear relationship, because droplet generated under the dripping regime is not linear, and it does not correspond to the proposed scaling equation. Instead, from our experimental results, we generated a new scaling model shown right there, where we have a new logarithmic term, and this is because an increase in flow rates of the continuous and dispersed phase liquid will lead to an increase in length droplet, but yeah, excuse me, sorry. So yeah, it's not linear. Right here we studied the effect of viscosity of the dispersed phase liquid, which was water, using an experiment, on the squeezing regime. So we can see two straight lines of results, but there's a little discrepancies on the green one due to several minor errors, which will be addressed later. And to do the experiment, we held the flow rate of oil constant at a relatively low flow rate, changing the water flow rate, and the result shows that an increase in viscosity of our dispersed phase liquid will not lead to an increase in dimensionless length droplet. So this also validates the fact that the scaling equation is independent of the viscosity of the liquid used. Now, to conclude it, to make conclusion, we concluded that under the squeezing regime of droplet generation, the Laplace pressure balance between the two immersible liquids prevails over the cross-flow shear stress. So the scaling equation proposed at the start of the experiment was only valid for droplet generation under the squeezing regime instead of the dripping one. And we generated a new model from our experimental results for the dripping regime. So in a nutshell, we can say that the droplet generation emulsion in the squeezing regime has to create more stable emulsions instead of the dripping one. Lastly, we also studied that the scaling equation proposed for the squeezing regime is independent of the viscosity of the liquid. Under the conduct of experiment, we came upon several limitations that might cause inconsistency in our results. Therefore, we came up with several recommendations. Now, due to time constraints, we did not change the syringes that often under the same day of experimental conduct. So this might lead to swelling of the syringes used due to the minor vibrations of the pump. Now this might also lead to deviations of the flow rates, which will also consequently lead to perhaps inconsistency of our droplets generated. So a way to overcome this is of course changing the syringes more frequently. Besides that, there are also unclear images of the droplets. For example, the droplets generated under the dripping regime shown previously was quite unclear. Now this might be due to limitations of the light on the microscope, or the image resolution of the camera was not high enough. So we can simply overcome such a thing by using high-speed camera with high megapixels. Now we can provide slow motion analysis, which will have better images of high value. So lastly, we can also study the effect of viscosity on scaling equation under the dripping mechanism instead. This can further justify that scaling law has no relation to droplet generation under the dripping regime. That will be the end of today's presentation. Thank you for attention. Excuse me.
All right.
Yeah.
Thank you. Nice job. About a minute over. Probably could have wound up a bit at the end. That's all. I have a few questions. Do you want to start? Or you want me to?
I'll start. What was your droplet size in this weekend? Approximately.
In micrometers? In squeezing regime, it depends on the flow rates of the liquids used. So the higher the liquid flow rate, higher the but it's approximately around, probably around 10 micrometers, we have around 300 micrometers size, the length of droplet.
And how many drops did you sample to book that graph?
So for every ratio of our dispersed and continuous space peak, we took a sample of probably 6 samples, and then we take an average of the sample.
6 drops?
Yes, 6 drops.
Isn't that sufficient?
It is sufficient due to time constraints because the droplet generator was quite constant. Yeah. So
did you do a drop size distribution at all?
Sorry?
Did you generate a drop size distribution?
Drop size distribution? No.
Could you explain to me what the Laplace force is? You said it's balancing the shear force. I didn't quite follow what you meant by that.
It is it's basically the Laplace pressure inside the droplet. This is based on the interfacial pressure between the water and the oil side, I suppose.
How is the Laplace pressure related to the radius of the drop?
Not too sure that's
It's inverse with radius. The Laplace pressure, so as the drop goes up in size, Laplace pressure goes down. So is there really a Laplace pressure in your drops that's significant?
The Laplace pressure, I guess no, we didn't study the effect of the Laplace pressure in this way.
So, but you do say the Laplace pressure is related to interfacial tension, that's correct?
Yeah.
So then you also said your scaling relationship isn't a function of interfacial tension. So can you explain, those are contradictory observations? Could you maybe rationalize that?
I guess the pressure, the Laplace force is only affecting the regimes, how the droplets are generated under specific regimes. So the scaling equation is independent of the interfacial tension in the sense that it only studies the length of the size of the droplet generated. So it does not matter whether the Laplace force or the cross-version force is exactly.
Is there a restriction on where you can use your scaling relationship?
A restriction?
Yeah. So you kind of said it, right? You said that the interfacial tension is important. What's the limitation? I can't imagine the interfacial tension is never important in flow. So is there any limitation on the flow conditions you can apply your scaling relationship to? There is one. There's a capillary number range.
Our capillary number is,
Could you show me your logarithmic correlation? Okay. Did you try fitting your linear correlation to any part of that data?
linear, oh yeah, but it does not correspond to a linear relationship because they are discrepancy and the results, they are scattered, the results are scattered. So
would you expect a linear correlation to be more appropriate on, say, the lower Q ratios?
lower, yeah.
Did you try fitting just part of that data to a linear correlation?
No, because the ratio, the flow ratios were high, so the capillary number was higher than the 10 power negative 2. So instead, it did not show a linear relationships compared to the squeezing regime.
Okay.
So
the geometric basis for justification for that particular functional form?
sorry.
What's your basis for coming up with a logarithm other than it fit the data?
The alpha constant?
Well, you have the log of the flow rate.
Oh, it's generated from the graph.
There's no physical basis for that. Remember, the other scaling relationship you use is based out of the geometry of a T-junction and a mass balance on flow. That logarithmic term is empirical then?
Empirical to the geometry of the...
Yeah, that's not derived from any mass balance arguments or conservation of volume or anything.
We did not. Yeah.
One of your conclusions was that your results are independent of viscosity.
Yes.
Do you think that's a valid statement, even that you only had a narrow range of viscosities? Do you think there would be a case where viscosity will be important?
Well, we did study that under the literature reviews that it is independent. So we deem it as valid because yeah.
Could you not have clarified the statement saying within the range studied? Okay, you never make an open statement like that. That's not important. And one other thing, you mentioned about swelling in the syringes.
Yes, syringes.
What's in your syringe?
So it's just the liquids contained in syringes.
Yeah, well,
So swelling there's a rubber in the syringe. So due to minor vibrations, it might be due to minor vibrations of the pump, it might pump the syringe a little bit faster than the set point of the flow rate. So that might be an issue, might be an error.
But that's not swelling of the syringe, is it? Well, what's in your syringe?
It's basically just oil and water inside the syringe.
So one has canola oil,
One has canola oil.
So which syringe is swelling? Both or just one?
The oil, mostly the oil.
So you're saying your rubber seal.
And then it's because it's connected to a pipe, a small little pipe, connected to the T-junction device. So it might also cause leaking, which is part of might lead to losing part of our materials, so might affect the flow rates of the...
Why didn't you use a glass syringe?
A glass syringe? Oh, we did not have that.
Thanks. You're done? You're done now, right? Congratulations, you're an engineer. Just some quick feedback on your talk. You were well spoken. In a 15-minute talk, one, I don't think you need to spend nearly as much time being magnanimous about, as gracious about the acknowledgments at the beginning. Sucking up doesn't help anyway. And you don't need an outline slide for 15 minutes. Everyone knows you're going to have an introduction, results, conclusion, the discussion and conclusion. So those you don't normally need. If you were going to have those, it would be because you're trying to, I'm going to, in the introduction, tell you something about this that you want to highlight or the results. I'm going to show you this amazing result.
Otherwise, you really don't need it for a 15-minute talk.
All right. Thank you. Do you have an electronic copy of your report?
Yes. Okay. Oh, no, I don't.
Please forward that on.